chapter 4 of the matrix operations book. So chapter 4 is about matrix inversion. And so before we introduce the matrix, in how to do the matrix inversion, we have to look at what do we mean by identity, matrix identity. This is actually the multiplicative identity, but it is often just called identity. So an identity matrix is a square matrix with all diagonal entries as 1 and all of the diagonal entries or non-diagonal entries are 0. It is denoted by I or I sub n. So here are two examples of the identity matrix. This is a 2 by 2 identity matrix, and the other one is 3 by 3 identity matrix. Note that when you multiply a matrix with an identity matrix, whether on the left or on the right, you will always get back A, and that is the purpose of the identity. So this is the similar thing in real numbers. We have the number 1, that is the multiplicative identity, because when you multiply any real number by that, you get back that real number. Okay. So here, example is saying show that AI is equal to A and IA is equal to A, where A is equal to this. So if we have this matrix and you multiply it with identity matrix, for example, first we do AI. So I'll write it maybe over here, AI. So we write our matrix A, and then I multiply with identity matrix. So we get 1 into 1 is 1, and then times 2 into 0 times 1 into 0, so we get back 1. Then we multiply 1 into 0 plus 2 into 1 plus 1 into 0. So we get 2. Then I multiply this with the third column of the identity matrix, so I get back 1, which is the first row here in our A matrix. So it looks it's going okay. So now a second row and first column, so we get 1 plus 0, 0. So we get 1. Then second row and second column. So we see that we get 3. And now second row and third column we get 2. Now we have the third row and first column, so I get 1, and a third row and second column, so I get 0, and third row and third column I get 1, which is the same as A. And you can now show this on your own. So put the identity matrix first. And then the A matrix, and multiply out. You will notice that you get back your A. Okay, now let's talk about the matrix inverse. So given a square matrix now, so it should be clear now that matrices, if they exist, the inverses, if they exist, they will exist only for square matrices. So given a square matrix A of size n by n, a matrix B of same size is called the inverse of A, written as this, or just A inverse. So we call it A inverse or inverse of A, and it is denoted by this notation. So if B times A is the same as A times B is equal to the identity matrix. Now note here, this product generally doesn't hold, but this statement doesn't usually hold, but for the matrices and their inverses, this always is true. Or instead of that, we can write it like this, because we know that A inverse is the inverse of A, or B is actually the A inverse. So not every matrix possesses an inverse. A matrix that has no inverse is said to be singular, or sometimes we also call it non-invertible. And a matrix that has an inverse is called non-singular or invertible. Knowing the inverse of A helps us find the solution of the system of equations when written in the matrix form Ax is equal to B. Now I will be using the small letters for x and b. So my equation will be like this, and then the same thing that we multiply on both sides by inverse. But remember, in matrices you have to be careful. If I multiply by A inverse on the left, here, then I cannot put A inverse on this side. I have to put it over to the left of the B. So this is equal to A inverse B. But now A inverse A is I, so we get I times x is equal to A inverse times B. But I times x will give us back x, so x is equal to A inverse into B. So this way we can find our solution of the system of equations. Now, how do we find the inverse? So this is one of the methods. So we will use the row operations on the matrix, and remember there are 3 row operations allowed which are given over here. So the step 1 for finding the inverse is augment the identity matrix I with A as, so put it like this, so A and then line, vertical line, and then put the identity matrix. Perform row and operations to convert A into identity matrix, so the above matrix looks like something like this. So what we do, our goal is to make change A into an identity matrix. So we do row operations to put this into the form of identity matrix. Then as we do operations on this side, simultaneously we will be doing the operations on this matrix as well. So this will end up coming a completely different matrix than what we had started with. So this will be the A inverse matrix. So then B is equal to A inverse. And then you can check by multiplying this matrix A inverse with A and see that you get the identity matrix. Then it means you got it correct. Some property of the inverse, that the inverse of a non-singular matrix is unique. Now inverses are always unique, okay, no matter what thing we are talking about, but here we are talking about matrices. So inverses of a matrix, but inverse of a number, inverse of a vector, inverse of a any other thing that we will talk about is always unique. Okay, if A is non-singular or invertible, then the inverse of A inverse is A. So if you take the inverse A inverse and then take the inverse of A inverse, then we get back our matrix. So this tells us that both, if you have this situation, A times B is equal to I and B times A is equal to I, then A and B are inverses of each other. Now if A and B are non-singular matrices, means they are both invertible matrices, then A times B whole inverse is equal to B inverse times A inverse. So this is a little bit different than usual things you have seen. So when we distribute this inverse sign, it gets inverted. The product gets inverted. Number 4, if A is non-singular, then so is A transpose. So if A is invertible or inverse of A exists, then inverse of A transpose exists, and the inverse of A transpose is the same as if you transpose the A inverse. Okay, so here example, find the inverse of the matrix A, where A is in the first case a 2 by 2 matrix. So we will augment a 2 by 2 identity matrix here and perform a row operation. So we have the first thing I want to do is bring a 2 here, 1 here. So this will be our pivot. So we want to make it a 1. So what do? I can do different things, but here I am just multiplying the first row by 1/2. So I get 1, 3 halves, 1/2, 0. Because we apply the operation on this side as well. So then I will, my next job is to make this a 0. So in order to do that, I will multiply the first row by -1 and add it in the second row. So negative R1 plus R2. So this gives me 0 here. Then negative 3/2 plus 2. So this gives us 1/2. So that's what I have here. Now applying the operation on the the other one piece. So I have to multiply the top row by -1. So I have -1/2 plus 0. So it gives me a -1/2. Okay, sorry here. And then next thing is 0 times -1, which is a 0 plus 1. So it just gets 1. Then next row I have to make this number a 0. So what do? I use this as my pivot. So multiply by -3. So it gives me -3/2 plus so I get okay plus, so this makes it -3/2 plus 3/2, so it makes it 0 here. That was my goal. But on this side, so when I have multiplied this by -3/2, -3, now we multiply, so -3 R2 plus R1 is giving us this step. And now just make this a 1, so multiply by 2. So this is our A inverse, and you can check by multiplying with the identity, with the actually not the identity matrix but with the A matrix, and you do it on both sides and you'll see that you end up getting an identity matrix, which means we got the inverse correct. Same thing over here. So in this matrix, so the first term in the first row and the first column is -2. So I would like to start by making this a 1, which I can do in different ways. So this time, instead of multiplying by 1/2 or -1/2, I am just going to add the third row in the first row. So this will be 3 minus 2, which will be 1. So that's what I do. And I take the third row and add it in the first row, keeping my third and the second row as it is. Nothing going with those. And you can see how the process goes on, and you get identity matrix here. Once we got that, then it means this side is A inverse. So that's what I have here. And then I check. I've checked only from multiplying by only on one side. You can check the other product. How do we use these inverses for solving a system of equations? So solve the system of equations using the matrix equation Ax is equal to B. So remember, we have looked at it like this. It doesn't matter, these are just names. So I say, okay, this system can be written as Ax is equal to B, where A is the matrix of the coefficients, which I pull from these equations, and here is my A. X is the matrix of the variables, and the B is the matrix, the vector of the numbers on the right of the equal to sign. So now we apply in our equation. So we just noted that X, once we have this, then the solution will be X is equal to A inverse times B. So that's what I'm going to do. So A inverse, if you note, this matrix is the same as what we just, whose inverse we just found in the previous example. So I'm just going to take that inverse over here directly, not going to redo the whole thing because this will be the same thing. So then use it like this. X is equal to A inverse B. So here is my inverse matrix, and here is my B matrix. This is the A inverse, and this is the B. Multiply it out, this is what you get. So what does that mean? Because X is the XYZ, so we get X is 3, Y is -6, and Z is equal to -1. So this is how you solve these equations. Okay, that's it for chapter 4.